Before we go into Lagrange theorem, let's understand what a group is in group theory. A group is a set, usually written as G. Together with a binary operation, we can think of it like addition or multiplications that takes two elements from the set and give another element from the set. For something to be called a group, it has to follow three main rules. First, associativity. This means that when you take three elements from the group, let's call them A, B, and C, the way you group the operation doesn't matter. In other words, a multiply by the result of B times C is the same as the result of A times B then times C. The formula on the slide show this as A times in bracket B times C equals in bracket A times B times C. Second, there must be an identity element. This is a special element in the group usually called E. That doesn't change any other element when used in the operation. So E times A is still A, and A times E is also A. In symbols, identity times A equals A and A times identity equals A. Third, every element must have an inverse. This means for every element A in the group, there exists another element called the inverse of A, written as an inverse such that when you combine with inverse, you get the identity element. So in symbols, A times A inverse equals identity, and A inverse times A also equals identity. So overall, a group is a set with an operation where these three rules always true: associative, identity, and inverse. This structure is the foundation for many important theorems in group theory, including Lagrange theorem, which we will talk about next. So before we dive into how Lagrange theorem works, let's understanding group and subgroup. First, a group G is a set of elements with a rule for combining them, and this rule follow four properties: closure, associative, and identity element, and inverse. Next, a subgroup H, a smaller group inside G that still follow all the group's rules. The order of a group written G is just how many elements are in it. Same for a subgroup, H is the number of elements in H. Next, let's talk about the order of an element in a group. The order of an element means the smallest number of times we need to combine it with itself to get the identity element. So if we have an element A, we're looking for the smallest positive number n such that A to the power of n equals E, where E is the identity element. If no such number exists, we say the element has infinite order. Let's see an example in the group Z6, which is integer mode 6 with an addition. Let's take A equals to 2. If we add 2 3 times, 2 plus 2 plus 2, we get 6. And mode 6, that's the same as 0. Since 0 is the identity in this group, the order of 2 is 3. So we say the element 2 has order 3 in Z6. Lagrange theorem tells us that the order of any subgroup must divide the order of the group. For example, in the Z12, the total number of elements is 12, so the possible subgroup size are number that divide 12 like 1, 2, 3, 4, 6, and 12. One example is the set 0, 4, 8, which is a subgroup with 3 elements, 3 divided by 12, so it follows the rules. Next, if a group has prime order like 7, it always cyclic and simple. This means that any non-identity element can generate the whole group, and there are no proper subgroup. However, not all divisor give subgroups. For example, the group A4 has 12 elements, but there is no subgroup of order 6 even though 6 divides 12. Lagrange theorem also applies to elements. The order of any element must divide the group's order. In Z10, the element 2 create the subgroup 0, 2, 4, 6, 8, which has 5 elements and 5 divides 10, so it's work. Lastly, group can be split into equal parts called cosets. If a group has 8 elements and a subgroup has 2 elements, then we can divide the group into 4 cosets, each with 2 elements.
So now I would like to share about the statement of Lagrange theorem, which is if G is finite and H is a subgroup, then order of H divides order of G. Finite group G. G is the element of group G, subgroup H. H divides G means H size fit evenly into G size. This means G equal to K times H for some integer K. This means there exists an integer K. Okay, that is for the intro for this Lagrange statement. By using this visual, we can see that this basically means H is inside of G. Now, for example, if G has 12 elements, G can only have subgroup that divide 12, which is 1, 2, 3, 4, 6, and 12, because this is the factor of 12. Now, moving on to coset. What is coset? For a subgroup H of a group G and an element G in G, the right coset of H with respect to G is Hg equal to Hg H in H. Cosets are subsets of G formed by multiplying H by G. All cosets of a subgroup have the same size as H because the number of elements won't change, just the element will change the value, but it will still stay in group G. Now let's go to cosets partition of group. Let G 12 and H is 4. Then 12 divided by 4 will be 3, will be the cosets partition. This means there will be 3 cosets because the cosets are disjoint and cover all elements of G. This basically means that we divide the G into 3 similar smaller groups that is called coset. Why cosets matter in Lagrange theorem? Now going back to earlier Lagrange theorem statement, if G is finite and H is a subgroup, then order of H divides order of G. Cosets satisfy this statement because cosets divide G to H, which has similar element in all of them. This means that G equal to number of cosets times number of elements in H, which example that we use is 3 times 4 equal to 12.
So let's look at 2 important lemma related to coset in a group theory. So we will begin with lemma 1, which talk about the right coset. So for any element A in a group G, the right coset HA is defined as the set of all element X in G, such that A is congruent to modulo H. Mathematically, we will write it as the given in the slide. Moving on to lemma 2, which state that coset partition to the group. This means that all right coset of H in G have the same number of elements as H, do not overlap with each other, and together they cover the entire group of G. So in other words, the right coset divide the group G into equal, non-overlapping pieces. So we will move on to the next slide. Now let's see how Lagrange theorem is proved using cosets. Let G be a finite group and let H be a subgroup of G. We form all the right coset of H in G. This coset look like HA1, HA2, HAK. So here each A1 to AK is a representative from G for its coset. By lemma 2, we know 3 things about these cosets. First, they are disjoint, meaning there no overlap. Second, each coset has the same size as the subgroup H. And third, together they cover the entire group of G. So the total number of elements in G is just the number of cosets K multiplied by the number of elements in each coset, which is modulus H. That gives us modulus G equal to K times modulus H. This means the order of H divides the order of G, or we can say modulus H divides modulus G, which is the statement of the Lagrange theorem. So let's go through an example to understand coset Lagrange theorem. We start with the group ZC, which have 6 elements in the set, which is 0, 1, 2, 3, 4, and 5, which is the integer modulo 6 under addition. We take a subgroup H, which have 2 elements, 0 and 3. These are elements that form a subgroup under addition mode 6. Now we compute the right coset of H. 0 plus H equal to 0, 3. 1 plus H equal to 1, 4. And 2 plus H, which is equal to 2, 5. If we keep going, 3 plus H, 4 plus H, 5 plus H. So we can see that all coset are disjoint and have a equal size, which is 2, and it is same size as H. So this coset form a partition of Z sets. Z sets equal to H union 1 plus H union 2 plus H. Finally, this illustrates a Lagrange theorem, which say at the order of the subgroup 2 divide the order of group 6.
Moreover, I would like to talk about its consequences. There are 4 consequences of Lagrange theorem. First one is subgroup order must divide the group order. This restricts the possible size of subgroups and is a key structure constraint in finite group theory. Second one, the order of any element is a divisor of the group's order. Third one, finite group have predictable structure. Knowing the group order help identify what kinds of subgroups and elements it can contain. And the last one is useful for proving non-existence of subgroups. If a number doesn't divide the group's order, it's definitely no subgroup of that other exists. And the next one, I would like to talk about its application. Why do we need to care about the application of Lagrange theorems? There are 5 reasons. The first one is algebraic structure classification. It helps in understanding and classifying finite groups by analyzing the divisor of their order. The second one is cryptography. It forms the basis of many public key systems such as RSA and ECC, where group structure over finite fields are crucial. And the third one is number theory. It lays the groundwork for Fermat's-Little theorem and Euler's theorems, both foundational in modular arithmetic. And the fourth one, abstract algebra and Galois theory. It's commonly used in studying field extension, solvability of polynomial, and understanding symmetries in equation. And the last one is combinatorics and permutation groups. It's very useful in analyzing symmetries, group action, counting distinct configuration in puzzle like Rubik's Cube. That's all. Thank you very much.